All right. I figured out kind of too late in the semester. You know how I've been using my laser pointer? You know, that doesn't show up on the video, which is kind of shitty. Y'all should have mentioned that a long time ago. I mean, I knew that, but I just think so. I put this in here where I have a pointer instead, and I can take it off. And I've had it the whole time. Oh well, because you can barely see that, right? I mean, that popping around. And then check this out. If I went, whoa, I can do that, and then I can do that. Sorry. Oops. All right. Next time, next semester, I'll get it next semester. Wish we could unlock that. Okay, so mini exams. Everyone's got the mini exam turned in, and the bonus. And I have the mini exams for you. And why don't you just get these at the end? Is that all right? That way we can focus on today. We'll pass these out, or not pass it at the end. You can come get. Don't forget too. Please remember to come get these, because then I'll have more stuff I don't want to carry. All right, this is where we ended last time, right? We started out talking about, check it out, line integrals over vector fields, right? And what I was trying to convince you of, I'm not sure if I convinced you or not, was that if we have something moving along a curve, point moving along a curve, it has a tangential component, like where it's headed. Then there's the vector field, which is having basically a force being applied upon the point. And that if we take the dot product of the force vector and the tangent vector, it gives us work, remember? But we said we had to scale the tangent by the infinitesimal length, which we said, you all remember what that was going to be called then? ds. So I did edit the notes. The ones that you have in front of you, I went home and I changed it to make sure that it really kind of followed what I was trying to say. So if you look at 13.2.16, I put in there this different sort of order of things. Crappy one. Yes. So what I'm trying to say is that I added that little ds in there. That ds is a number, all right, and that number scales that tangent vector. So we get that the work is the line integral of the vector field f dotted with the tangent vector times ds. And ds is arc length, right? All right, so remember r of t is a vector function. What is r of t? I mean, it's a vector function, but what is it? Yes, it's the curve, right? It draws c for us. And that gives us some restriction on the t of, you know, a and b. Capital T, that vector is the tangent vector, and f is that given vector field. So that's just defining what everything is. Now, this is where things get kind of cool. Since the tangent vector is the derivative of the vector function divided by its own length, and since ds, what's ds? It's arc length, right? You can go back in your notes. Arc length, we talked about last time. The arc length of a vector function is the magnitude of its derivative. So if we go back and we look at this formula right here, we have f dotted with t ds. The f is just f, right? T is r prime over its magnitude. And then ds, we just said, was r prime magnitude dt. These r prime magnitudes cancel, don't they? And if they cancel, what you should be left with then is f dot r prime t. Agreed? dt at the end. But I threw something, instead of f, I put f of rt dot r prime t dt. So I added this to your notes. It's not down there. What f means, what f of r of t means, it's your vector field evaluated on your curve. That's all it is. You take your vector field and you plug in the parametric equations into your vector field. So when you see f by itself up here, that really means f evaluated somewhere. You can't just have the vector field without evaluating it. So where do we evaluate it? We evaluate it on the curve. And this new integral right here with limits of integration a and b is the one that we use most often when we're trying to compute work. We use this one. We don't go try and find the unit tangent vector. We don't do any of that because that tangent vector part, that length there, cancels out anyway, right? So why go do all that work? With me? All right, next. Now the general definition. Suppose f is a continuous vector field defined on a smooth curve C, where C is parameterized by R of T, A is between, T is between A and B. Then this is what we call it, the line integral of f along C. Here f is a what? Vector field, right? It's a vector. It's a field, but we were doing line integrals along little f, right? And little f was a scalar function, not a vector function. So now we're actually integrating vector functions. Now we're still integrating them along a curve C. And here's the new notation. This right here. Integral over C of capital F, the vector field, dot dr. Now dot dr, just so you know where this comes from, we're going to look at dr right here is really r prime t dt. And one way you could look at it is, oh, wrong one. When we say dr dt, right, we're given some vector function, r of t, on the right side there. When I say dr dt, that means take the derivative, right? And now just take dt, kind of like multiply both sides by dt. So that dr by itself in this formula right here is this piece right here. So this is notation, all right? This right here means this. This capital F by itself means this. And then our limits of integration a and b. Now we also said the whole motivation for this came from this f dot the tangent with respect to arc length. So the one in the middle that's boxed is the one that we'll be using most often. So here's our first example. Find the work done by the gradient vector field of f of xy equals x plus y squared on a path traversing the top half of the unit circle in a counterclockwise direction. So just for the picture, here's the vector field. We're starting here, top half of the unit circle. We're going to move our way around counterclockwise. And while we move, right, as we move this thing, there's work being done, and we want to know what the total work is. Now, remember that the work is the dot product of the force and some scalar multiple of the tangent, right? So it's like a dot product of the green one or a scalar multiple of the green one and the red one. Remember that dot products, when the angle between the two vectors is less than pi over 2, the dot product is what? Positive or negative? Positive. If the angle between the two is greater than pi over 2, it is negative. So it is possible to have negative work because the dot product can be negative. Keep that in mind because I think the answer to this one's going to be 0. And you might be like, what? How can you have no work? Yes. It's not that you're going opposite direction. It's that the force vector. See the red vector there? Is actually the angle between these two vectors is greater than 90 degrees. Does anyone remember the formula for dot product? Like there was a formula that involved the trig function, cosine theta. So it was, if you take a vector u and you dot it with v, u dotted with v is equal to magnitude u, magnitude v, cosine angle, where the angle is the angle between the two vectors. So cosine, because cosine, right? Anything less than 90 degrees, cosine is positive. Anything greater than 90 degrees, cosine is negative. And then, of course, the first two pieces here are always going to be positive. So it is possible to have a negative dot product. That ring a bell? So right now, if I were to look at the work being done at this instant right here, at that infinitesimal little piece as I move, my work there would be negative, wouldn't it? Or what I'd be integrating, right, would be negative. All right, let's go ahead and do this. So here's what I'd like. I'd like to find the total work done, right? So I want the integral over some curve C of f dot dr. I will be looking for on your next mini exams, which I don't have right now, I will be looking for proper notation. That capital F is a vector, so it needs to have some vector notation. You can't just use capital F. If you don't use vector notation, then it's not a vector, it's a scalar function. And your differential here, dr, that's a vector. It's the derivative of the vector function r. Understand? There's a difference. Okay, so that's what we want, right? Let's talk about the curve first, because I think the curve is the cleanest part of this. The curve C is the upper half of the unit circle. And we've done this so many times, right? We should be able to parametrize that pretty much in our sleep. R of t, well, let me do it this way. What we said in the past was this. X was what? Cosine t, and y was sine t. And then we said the restriction on t was 0 to pi, right? Well, in order to do this problem, I need r, don't I? I need a vector function, not x equals and y equals. So what I'm going to do now is I'm going to convert this into a vector function. And there's no work that has to be done. I'm just going to write it like this instead. Cosine t, sine t, like that. That draws the same thing, doesn't it? Okay. Now, what's valuable about that is I'm going to need to, at some point here, going back to my notes, I'm going to have to take the derivative of that, right? And I'm going to have to take that vector function and plug it into what? My vector field. So shall we, while we're here right now, go ahead and take this derivative? Okay. So my derivative is the vector function, negative sine t, cosine t, right? That's all I think I'm going to need. Right? I have my limits, 0 to pi. I have my r of t. I've got my r prime of t. What don't I have? The vector field. But let's read this question carefully. Find the work done by the gradient vector. Wait a minute. Little f of xy, right? Little f, scalar f of xy equals this is not a vector field. But, what am I saying? The work done by the what? Gradient vector field. Do you remember what the gradient vector field is? It's the vector field that you get when you take the gradient of the scalar function. So what we need to do is take the gradient of this. So in this problem, I'm not just handing you the vector field. You have to remember what a gradient vector field is. So going back to the notes here, my capital F for this problem isn't given, but I'm told it's the gradient vector field. So it's the vector field created when you take the gradient of F. Remember, given any scalar function, you take its gradient, and it creates a vector. So what is the vector function? Or sorry, yeah, the vector field that we'll get. So do I remember what this is? It's the partial of F with respect to X, and the partial of F with respect to Y. And now I don't have a Z because this function was only in 2 dimensions. Right? This function only had X and Y. So since you have that in your notes, what is the partial derivative of F with respect to X? 2x plus Y? What's the partial of F with respect to Y? Same thing, right? 2x plus Y. That's capital F. Questions? I'm pretty much ready to go here. So this integral will become the integral from A to B of the vector field F evaluated at R of t dotted with R prime t dt. Now it's just a matter of plugging things in. So integral from 0 to pi. This piece, f of R of t. All I'm going to do is take this f right here that I just got. I'm going to replace my x with what? The parametric equation for x, which is either up here, x equals cosine t, or reading it right off of R of t, it's right there, cosine t, right? So I replace the x with cosine t. I replace the y with what? Sine t. And it's a vector, isn't it? So here's what it'll look like. It's the vector 2 cosine t plus sine t. Okay, the next component of the vector field is the exact same thing, isn't it? So 2 cosine t plus sine t. Close off my vector. I'm supposed to dot that with what? The derivative, right? So the derivative is negative sine t cosine t. Then dt. Any questions? Remember how to do a dot product? When you take the dot product of 2 vectors, right, all you're doing is multiplying their components and adding them up. And your answer should be a scalar, right? Dot products of vectors is a scalar. Cross product of vectors is a vector. So let's go ahead and do this. I'm going to have to multiply 2 cosine t plus sine t times negative sine t. I have to multiply 2 cosine t sine t times cosine t, and then move everything around, right? Well, fortunately for me, I did that already. Here it is. So I multiplied that all out, and when I did, I got some things to cancel. And then all I was left with was these 2 terms in the middle. And then I factored a 2 out, and then I looked at that, and I said, hey, wait a minute, pre-cal, that's like a double angle formula for cosine. Cosine squared t minus sine squared t is cosine 2t. So I got that and put it here. And then I integrated this trig integral here. Pretty simple integration. And then evaluated 0 and pi, I get 0. Okay? I don't expect for us to work that out now. But you got it? The setup was all done. Once you got it to the integral from there, it should just be pretty straightforward. Are there any questions, though, on the setup of any of this? Where any of this came from? I love that arrow. It's great. No? I can make it less transparent or more transparent. Would you like to? I can make it bigger and smaller, too. I can't change the color, though. Yeah. Yeah. As far as I know, those are my only... Oh, wait. Oh, no, it's a pointer. I can change my highlighter. All right, come on. Let's get back to this. All right, let's get back to the notes here. So the total work done was 0. And that's kind of weird because you would think, look, if you move something, right, in a vector field, you're going to have to do work. Well, some of the work is negative, considered to be negative work, so it's 0. That's okay. It's okay to happen. It's okay to get 0 work. We'll see later that, you know, if you have like the Earth and you have something in like a circular orbit, there's actually no work being done. There's actually no work is required or is being done by gravity moving this around. It's kind of strange. Network, sorry, net total. 1 rotation. Double match. Oh no, did I miss? No, I did it. See what you've done. Oh, my goodness. Might be. Okay, here we go. So now we have another one. This time I don't mess around. I just give you the vector field. Okay, so I don't say, oh, the vector field is the gradient vector field of this function. I say, here it is. Boom. There's a vector field. And I want us to figure out the integral of that vector field over that curve C on this parabola. So here's a picture of it. Move it around. What work is being done? Now, again, I already did this problem, so I'm just going to go straight to showing you the work for it. And let's just see if we can follow through with this. All right, first of all, my parabola over here on the right side is y equals 1 plus x squared. And that's what it looks like. And I'm going from the point -1, 2, which is this point, to the point 1, 2, which is this one. And I come up with this vector function r of t to be t 1 plus t squared. How did I get that? Yeah, remember we said if we ever have an equation like old school, y equals a function of x, you replace x with t, and you replace y with the function rewritten, replacing x with t. So this is like our 1 plus x squared, and over here is our x. But we're doing everything in terms of t. T varies from -1 to 1, because t is the x, isn't it? So -1 to 1. And then since I need the derivative later, I just take derivative. Derivative of this, let's see, derivative of t is 1. Derivative of 1 plus t squared is 2t. That all clear? Pretty straightforward? Okay, now I need my capital F, my vector field, dotted dr. That means I go integral a to b, -1 to 1. What is this vector here? That's capital F, but what? Replaced x with t, right? X here with t, x here with t. Replaced all my y's with 1 plus t squared, 1 plus t squared, 1 plus t squared. So that's what's happening when we plug a vector function into our vector field. All the parametric equations go in. Why? What? Oh, I left the squared off right there. Is that what you're saying? Right there? Yes, I did leave that squared off. I think I picked it up later. Oh, no, I didn't pick it up later, but good eyes, good eyes. It won't change anything because I expanded that out later on, different way, and yeah, it's right. I mean, no, that was wrong, but this is right. This is right down here. Because I think I expanded that one, so I wasn't looking at the one that's a mistake. Okay, what is this 1, 2t? That's your r prime, right? Okay, then when you dot them, you do 1 times this one, which is itself, plus, right? No vector anymore. I do not want to see that on a test. Something where you got a vector after you do your dot product. And then you do 2t times this, so the 2t distributes over the top. Then put the common denominator together. Collect your like terms on top. And notice I expanded out what was under the root. Like I multiplied all that out. And when I did, I got t to the 4th plus 3t squared plus 1. And it just so happens that as bad as that integral looks, that the derivative of what's under the root is almost the top, except I'm off by 1/2. So I have to scale it, and it just becomes a basic substitution problem. It was intended that way, okay? It was designed to work that way. And then integration, plug in, you get 0. All this for nothing. But here's the thing. If we would have changed, let's say we would have changed the parabola to go from -1, 2 to, let's say, something like 2, 5, right? Then all that would change in the problem is your limits of integration, right? Which would change this 1 up here to a 2. And now you wouldn't get 0. So the fact that it was 0 is just coincidental. I probably, after I did the problem, I thought about, I should change that. But all my pictures were drawn and everything, and, you know, the work isn't, it was no work, right? All right. Now, according to your notes, I believe there's only one more thing in here, right? Suppose that F is equal to PQR. So F is a vector field, right? It has 3 components here, P, Q, and R. I want you to look at P as being a scalar function, like little f used to be, all right? Little f. And then Q is like a little g. And then R is like a little h. So they're all scalar functions, right? Each one of them individually create the components of your vector field. Then, if you want to do this line integral over that vector field, which is what we're just doing here, it turns out to be, without me showing you, the book goes through proof of this. It turns out to be this. What are those? What are these? Is P a vector field? No, and dx, right? dx. These were those traditional line integrals that we started this section with, right? We did start this section. There they were. Right, look at this. The line integral of f, little f, scalar f, along C with respect to x, had the little dx out there. This was this, with the little x prime t sitting outside, dt. And this is along with respect to y and then with respect to z. So this note here at the end, towards the end, is telling us that there is a way to take our vector field, instead of integrating over the vector field, we can break it up into 3 integrals over the components, the scalar function. So the components of the vector field. The first one with respect to x, second with respect to y, third with respect to z. And you get the same result. That could be useful sometimes. But more importantly, we'll use that later in trying to prove some other theorems. Okay, that's where the notes end, right, for you? Or it has homework, right? Yes? Do what? Yes. Yes. P, yes. That would be your P. That would be your Q. Exactly. That's P, that's Q. Well, remember what we said is that a vector field is said to be conservative if it is the gradient of some function. So if that is the gradient of something, then it is conservative, right? Was that what you were just asking? Mm-hmm. Yeah. Uh-huh. Mm. No, if we were to change this, use the formula I just gave you, this right here, our P would be its own function. The R of t would still be the same. Okay, our path would be the same. And x prime of t, okay, now this is three-dimensional. The example you just talked was one-dimensional. What you would do is you would find the parametric equations for c, which draws it. You plug for x into that function, which was x over square root of x squared plus y squared. You plug in the parametric equation for x, parametric equation for y, and then the x prime is the derivative of that parametric equation for x. It's not the derivative of something else. So it's still connected to R, that path. All right, now I took a problem that I thought you might find interesting and threw it in here. And for those people who are in physics or have taken physics, you might look at this problem and realize that there's probably an easier way to do this. But where's Luke? Where's our physics guy? Is he not here today? I thought. Well, he likes physics. Okay. So there might be an easier way to do this. As you'll see when we work it out, you'll see that. Well, wait a minute. Hold on. You're overcomplicating this. But the point of what we're able to do is more important than the fact that this might be able to be done easier. All right, so just let's follow through first. Let's do the problem, and then we will talk about what's valuable. A 180-pound man carrying a 20-pound tool bag walks up a helical staircase wrapped around a 20-foot radius cylindrical silo. If it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? Note, work is measured here in foot-pounds because the man is in pounds and the measurements are in feet. And also, remember that weight is a force. Your weight is a force, right? It's different than mass. Mass is one thing. Mass times the acceleration of gravity is weight. Have you all heard that before? Okay. So, here's my little animation. Sorry, I just had to put this together. Just had to draw a little guy walking up silo. Okay, there's our man. He's walking up. And so we have the path he walks is your R of t. That's your curve, right? Your vector field that we're integrating over is the only force acting on him, which is what? Gravity. His weight, right? Right, the gravity. So he has to actually fight gravity to go up this, doesn't he? Yes? All right. So let's try and set this thing up and figure out what total work is. But you see the picture, right? Now, I've already done it. Do you want me to just walk through it, or do you want to start from scratch? You want to walk through it? Okay. All right, here we go. So, first of all, the silo is 90 feet high. I was given the word problem. Has a 20-foot radius. Let's start by talking about the field. The field, the only force is gravity. So it's saying find the work. The problem said find the work. How much work is done against gravity? Against gravity. Not by gravity, against gravity. There's a difference. Exactly, which is why I want you to see that my force vector, right, my force field is 0, 0, 200. 0, 0, 200 is just a vector that points straight up. Has a magnitude of what? 200. Where does the 200 come from? The weight, right? It's the man, 180 pounds plus his bag, 200 pounds. So gravity is acting down. The force against that gravity is 200 straight up. So our force field, right, is very boring here. It's constant, 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 isn't it? But that's what gravity is. Okay? Now, if we, yeah, I mean, we're taking some liberties here. We're acting like, you know, we're on the surface of the Earth and the gravitational field is constant, and there's a lot of things that we could change here. Yeah, now 90 feet, we're talking, you know, tolerances that we can't even fathom. So, all right, so that's it. That's our force field, all right? Now, our vector function, R of t, well, we talked about this before, like a spring. How do you draw a spring? Well, we need to draw a circle that keeps going up, right? So the circle we get from doing 20 cosine t, 20 sine t, right? And now we need it to go up. But how do we make it go up? Because what has to happen is that we have to start, we have to go 3 rotations, right? Remember that in the word problem, that's what it said, 3 rotations, and be at the top. T is the measurement of the angle, isn't it? T is our angle measurement. I mean, when we're drawing it, T is really like the angle. So how much does T have to go through to do 3 rotations? 6 pi, 0 to 6 pi. Agreed? So what we need is when T is 0, we need to be at the bottom. And when T is at 6 pi, we need to be at 90. So notice how this would work right there. Look at 90 over 6 pi t. If t is 0, what do we get? 0. If t is 6 pi, where are we at? 90, because 6 pi and 6 pi cancel. You can also do like a rate times time equals distance. Distance is 90. Time is 6 pi. Divide both sides, you get a rate. But that's kind of, when I did that, I was like, I didn't really like that. I just like to think about it as, where do I need to start? Where do I need to start? What time do I go through? 6 pi. So just scale it by 6 pi. Z is, this right here is your, it's how high you are, right? At a point in time. You said, so T is really, okay, yeah, Z is your height. That's right. This right here, right? This right here is going to go right up in here. That makes sense, though? This is an important concept. The up and down part you have to get from the idea of the rotations. Rotations, 3 rotations, that's 6 pi. So I have to go from 0 to 90 in 6 pi. That gives us our R of t. Then differentiate it because I'm going to need that. And then I come down here and I set up the vector field integral here. The integral over that curve of f dot dr is 0 to 6 pi, a to b. The field, 0, 0, 200, dotted with the derivative, negative 20 sine t, 20 cosine t. And then when I took the derivative of 90 over 6 pi t, I just got 90 over 6 pi. And then when you dot that, isn't that pretty damn boring? 0, 0, and then 200 times this, 90 over 6 pi. Gives you 3,000 over pi. You missed it, man. We just did a physics problem, Luke. Okay. Well, you better hope that you never need to walk up a silo and need to know how much work you did. No. Okay, so 0 to 6 pi, and then here, and you get what? 1,800 foot-pounds of work. That's it. So let me ask you from this formula right here. Did it matter? Did the path that I traveled, did the x and y components of that path factor in at all? No, right? I mean, look at this. No matter what this would have been, or this, right? These two components, no matter what they were going to get wiped out by 0, 0. So they had nothing to do with it. So your work going up against gravity is really just a function of the displacement that you have vertically, which is why I'm saying, like in a physics class, you may not have approached it this way because you don't need all the other junk. But why is this, so why show you, right? Well, because in a different situation, you may not look at gravity as being straight down. Because really, I mean, think about it this way. The gravity on my head, I'll draw a picture. I'll draw a better picture for you. If I have the Earth, right? Let's say the Earth is here, which isn't even a circle, right? I mean, a sphere. It's not a perfect sphere. And I'm standing here, right? And let's say the center of the Earth from my head goes down like this, right? To the center. Well, if I move up, let's say I go stand on a ladder, now my head's up here, right? Then that is a different, it's not the same direction. I mean, it's not straight down necessarily. It may be off to the side a little bit. So the vector, the field may not, we're assuming 200, right? 200 straight down or straight up, but in reality, it may not be perfectly straight down or perfectly straight up. And maybe you want to be looking at something where you have a mass in one place and a mass in a different place and something in between them, and now you have vector fields, gravitational forces from more than one object, right? I mean, there is a gravitational force of the Earth acting on me, right? How about the sun? It's acting on me too. Now it's insignificant compared to the Earth, right? But in reality, our vector field representing gravity is not as simple as just one direction straight down. In most applications, that works, right? But in a more broad spectrum, you need a way of dealing with any vector field. See what I'm saying? So the physicist usually goes to the mathematician and says, we have this situation where we have force acting down and like that, we need some sort of general way of finding the total work or something like that. The mathematician goes, I tell you what, we're going to come up with a way of getting that work done in any field. Okay? Any vector field. You want to add things up? Here it is. And now we have a general formula. Now, if the vector field is simple, like 0, 0, 200, it's non-trivial. Or trivial, sorry. If the vector field is more complicated, it can be handled. Does that make sense or not? Mathematicians are always looking for like more ways to generalize, instead of these specific cases. A lot of times in physics, what you get, the formulas that you see in the book, are usually specific cases for Earth, for whatever, you know. Okay, I had another example that I thought might be interesting too. I guess I'm making everyone sick today. Go ahead, go throw up.
Just let me know when you got some stats.
Some stats, and we're going to do some quadruple integral statistics. All right, and let me fix that. A 10 kilogram object moves with a position function. R of t equals 2 sine t, 3 cosine t, t. Oh, wait, I forgot to change that. Oops. It's supposed to be sine, pardon. What was it? Sine 4t, sine 8t, t squared. Sine 4t, sine 8t, t squared. Whoa. Did not like that. I have no idea what I don't know what I just did. Yeah, I do. Whoa. What did I hit? I hit control. Let me try that again, see what happens. Whoa. Back. Okay. Jeez. I'm just going to say shift squared. It did not like control. Am I still recording? Yeah. Was that running? Yeah. And I want to change from 0 to 1. Okay, so this is the path right here. Some 10 kilogram object is moving along this path, three-dimensional space. Find the work done on the object during this time period. So here's a couple of things that we need to be clear on before we do this problem. We are not assuming that this object is living on Earth and that it has gravity acting on it or anything like that. We're acting like there is no force field of gravitation on this. So you just have an object moving in the universe. What's the work done if it has to move over this path? It's kind of a weird question, all right? I don't think it's going to be 0. So let me set this up here. First, we're going to remember this right here. Maybe remember it, maybe not. What is that? It's one of Newton's laws, right? Force equals mass times acceleration, right? What we are given in the problem is a position function for this weird thing, sine 4t, sine 8t, t squared, right? T is between 0 and 1. And then what? The first derivative of this, right, is the what function? Velocity. This is a Cal1 thing, right? First derivative of a function is its velocity. Second derivative is acceleration. So if I take the first derivative, I get 4 cosine 4t, 8 cosine 8t, 2t. And then I take the derivative again. This is negative 16 sine 4t, right? Negative 64 sine 8t, and then 2. And this is an acceleration vector function, isn't it? For that object. And I know its mass, right? Its mass is 10 kilograms. So I know that the force, right, being mass times acceleration, should be that vector right there scaled by 10. So scale it by 10 and you get negative 160 sine 4t, negative 640 sine 8t, 20. So I can look at that as my vector field. And I want to take that and dot that against what? My R prime, right? So I'm trying to do this. I'm trying to do this right here to find my total work, which is integral a to b of the vector field evaluated at R of t, dotted with R prime t dt. So we know what R prime t is, don't we? It's right up there. What is our vector function evaluated at R of t? That's this, isn't it? See, we don't have to plug anything in because the vector, the capital F, it's using t already. Like the capital F doesn't have x's and y's, and we didn't have to parameterize those x's and y's. So all we have to do is dot those two together. Now I did this already, but I did it as I was kind of falling asleep. So this is it right here. Let's see if I ever came to an end. Maybe I didn't. Sorry. I started falling asleep. So here it is right here. Here's that R prime. Oh, look at my arrow. Here's my R prime. And then I just dot these, so I multiply those together, right? And when I do that, I put them right here. I know it's kind of sketchy work. You really can't tell what this says. But this says, you know what, should I do it or what? I mean, I thought it was written better. This is sine 4t cosine 4t. It looks like tangent, doesn't it? Looks like tax. I was really falling asleep. And then when you do this, though, do y'all remember the formula, double angle formula for sine? Sine of u cosine u, or 2 sine u cosine u equals sine 2u. So that's all I did here is I converted sine 4t cosine 4t into sine 8t. But then I had to bring a half out front, so that cut this negative 640 in half. I did the same exact thing here, and then 40t is 40t. Then each one of these I integrated. Antiderivative of sine, antiderivative cosine, or no, sine again, antiderivative 40t, and then I plugged in and I got some numbers, and anyway, it's a number, okay, and that's your work. The main part of this is already done, though. It's where do you get the force from, right? The force came from the mass times the acceleration. Where does the acceleration come from? The second derivative of the position. Okay? All right, that's going to wrap up section 13.2. That's the homework assignment. I believe that homework assignment is accurate. Let me double check it. Did I ever give you anything from 13.1? I did, right? There's a couple of things I think I gave from 13.1, wasn't there? Yeah, I think I didn't. Let me see, 13.2. So yeah, this is not even the right page. Okay, so look, I tell you what, I will email you that assignment today or tomorrow for the 13.2. I also created something. This is let me see. That code's not too bad for this. This is a little thing that I built. Let me see, do I have anything up here? Oh, here it is, right here. This is the problem we just did. It was that x, remember the vector field? I gave you the vector field was x over the square root of x squared plus y squared, y over the square root of x squared plus y squared. Then we did the parameter was the curve was the parabola. Yes? It was t plus 1 plus t squared, and t went from -1 to 1. Well, this is the thing where you come in here and you put these in yourself. You can change your vector field, you can change your parameter, you can change your a and b, and then you just hit this little update button, and it gives you the answer. Now, remember I said if I changed it to 2, it would change our answer? Well, if I update that, that's what your work would be. Pretty cool little. And that'll work. I think I built one for, yeah, this is for 3-dimensional. So if you have x, y, z, and 3 parametric equations. I've offered all my code to everyone. No one has come to me for these things. So yeah, that's why I put these, because I have in the past had students who actually take the Mathematica notebooks and they can have them. I don't have a problem with that. And then they can use them whenever they want. So not on the test though. Yeah. That's a good way to check your work though, at home on a mini exam or something. Yeah, you just have to make sure you set it up right. Okay, I am done with 13.2. So we move on. It's 2 o'clock. Just don't go pull the fire alarm. All right. When? I walked out there like an idiot, thinking that the fire drill was the entire campus. So I was like, if I try and go that way, they're going to tell me to go out there. So I'll just go stand out there. And then after about 15 minutes, I walked through the woods and came around. Yeah. Yeah. Okay, what are the fundamental theorems that you've learned in your math life? Before the fundamental theorem of calculus. Anybody know the fundamental theorem of algebra? No? The fundamental theorem of algebra has to do with if you have a polynomial of degree n, there are exactly n roots. But they could include complex numbers. That's the fundamental theorem of algebra. All polynomials basically can be factored into n factors. Polynomial degree n can be factored into n factors. Or if you graph it, it'll have n roots, some of them being imaginary possibly. That's fundamental theorem of algebra. Fundamental theorem of calculus said there was a connection between the derivative and the integral, right? And there were 2 versions of it. But the one that we use the most is that the way that you can, the one that we use the most is this one. It says that the integral from a to b of f prime of t dt is equal to f of b minus f of a. This just says that if you want to integrate a function's derivative, that the integral of the derivative basically they wipe each other out, and you just get the function itself, and then you evaluate the 2 endpoints. Subtract. And that represented the area under the curve. But you could almost have written it this way, without the limits of integration. That's basically what it's saying. Fundamental theorem of calculus. So now we are talking about the fundamental theorem of line integrals. If C is a smooth curve given by a vector function R of t, we've seen this, nothing new. T is between A and B. And if F is a differentiable function of two or more variables. So now we have a function that has to be differentiable. And that function F is a, what type of function? Scalar function, right? Not a vector function. I'm turning on the lights because I'm getting tired. Right? Is a scalar function that's differentiable such that what? The gradient of F is continuous on C. That just means the gradient is defined on that curve. The gradient is a vector, right? A vector function. Then we have this. The gradient of F dot dr. So gradient of F there is just like a capital F. It's a vector field. If you take the gradient of that function dot dr, then you don't have to do any work really. You just have to evaluate the original function at what? R of B, and then evaluate it at R of A. What's that? What's R of B? What part of the curve? The end of it, right? The curve C is drawn by R, right? So the curve C, our curve C goes like this. I mean, 2 or 3 dimensions, our curve C is doing something, right? It starts here, this is R of A, and this is R of B, right? Because T is between A and B. So our curve starts somewhere and then ends somewhere, whether that be 2 or 3 dimensional. The fundamental theorem of line integrals is telling us that if you're doing this, all you have to do is evaluate your function at the 2 endpoints of the curve, which means what the curve's doing inside does not matter. Got it? But you have to be looking at the gradient of F for this to work. So in the problem that I had earlier, right, I gave you a vector field, the one that was x over the square root x squared plus y squared. I gave you that one. That was not necessarily the gradient of something. We never checked for that. So we don't know if this would have worked. You with me? But if that vector field that we have here is the gradient of some function, then we don't actually have to go through all the work of finding the dot product. All we have to do is evaluate the 2 ends. Okay. So if we actually think about this a little more, this line integral will always give you the same answer on any 2 paths that have the same 2 endpoints. So if I have a path that looks like that, I have another path that maybe does this, right? Maybe I have a third path that does this. The line integral over C of the gradient of F dot dr will be the same for all of those paths because they all have the same starting point and same ending point. But the condition is that what we're integrating over, right, the vector field, is the gradient of F for that to be true. Okay, so let's look at this one right here. Let f of xy be x squared plus y squared, and c is given by t sine t, t cosine t on 0 to pi. Find it. Y'all okay? Are y'all ready for Easter? Easter egg hunt? All Easter means at my house I got to clean up the backyard so kids don't hurt themselves. Okay, that arrow's pissing me off. We have f of xy. I do like it when I'm talking, but I don't like it when I'm having to write. Okay, so there's a function, right? And our r of t is t. What does t sine t, t cosine t look like? It's like a spiral. Yes. Because the t out in front of the sine and cosine is like the radius, right? That's like the radius in front and the radius in front, and the radius starts out at 0 and then gets bigger. So as you draw the circle, the radius increases, so it looks like a spiral. Do I not have a picture? It's okay, I don't think I need one. Okay, so we're being asked to find this. We're being asked to find the line integral over this C of gradient f dot dr. So what should I do? Take derivatives of stuff? What's the gradient of that? 2x, 2y. Is 2x, 2y nice, continuous, well-behaved stuff? Okay. Let me go back one step. If C is a smooth curve, I think we got a smooth curve here, don't we? R of t, spiral-looking thing. The gradient of f is continuous, which means that when we take the gradient, it's nice, right? Then this integral is just this, and you don't have to do any work. So I have all the conditions, don't I? Smooth R, nice gradient. So all I need to do is figure out what f of R of b is. Yeah, be careful to not say f of b because it's f evaluated at the end point of the curve minus f of R of a. Well, what's R of b, folks? What's R of b? For us, that's R of pi. And R of pi is pi sine pi, pi cosine pi, which is, what's sine of pi? 0. What's cosine pi? -1. So negative pi. What do you think it means to evaluate f at the endpoint? Well, R of b is a vector, right? But we've said that that vector really takes you to a point in the two-dimensional space. So when we say f of R of b, we really mean here what? F of R of b will really mean f of R of pi, which is f of zero negative pi, like a point. What is 0 negative pi? Plugged into f. Well, where's f? Up here, right? 0 squared minus pi squared, just pi squared, right? Now that's just R of b. So I'm going to go back up here where I was doing my work. This is pi squared. Now what's R of a? Yeah. So R of a I'll do down here. R of a is R of 0. R of 0 gives me the 0, 0 vector, doesn't it? So what's f of R of 0? What's f of 0, 0? Which is just 0, which means I get minus up here 0. So what's that line integral over that gradient vector field? Pi squared. Yeah, there's no work. Here's what's going to happen, though. I can almost guarantee this. I'm going to give a mini exam, or I'm going to give a question like this on the final, and somebody's going to go through and they're going to find the parametric, they're going to find the vector curve, R of t, they're going to take the derivative, they're going to get the vector field, they're going to plug in R of t, they're going to dot product them, they're going to work that all out, they're going to integrate everything, they're going to get to the answer, and the guy next to him is going to be on the next problem already because they just used this. And if you do it this way, it'll take you maybe 2-3 minutes. You do it the other way, it might take you 15. Or if the integrals are tough, it might take you longer. You follow what I'm saying? You got to know when you can and can't use this. Got to know when. Watch, let's just check our work. If I were going to check it with this little calculator that I had, I would use, for my vector field, what was my vector field? What was the gradient of that thing? 2x, and then the other one would have been 2y. Yes, I want you to do this. 2y. What would the parametric curve be? Well, that was given, right? T, was it cosine t? It was 2 sine t. And it was t cosine t. And t went from 0 to pi, right? My answer better be pi squared. It is. Okay? Good thing it was. Let me tell you something real quick. I'm going to pause this because I don't want to catch it. I don't want this. Okay. Back to this. What? Oh, here it is. It didn't go away? No? I'll tell you what it's all about lately. It's all about work ethic, man. Work ethic is so hard to get you all to understand. I mean, I'm nothing like personal or anything, but work ethic, when you have students that have work ethic, those are the people who are going to do well, you know? And it's just so hard to come by nowadays. It really is. I mean, it really is hard to find students who really understand what it takes, you know, the time that's required. You know, like I was talking to my neighbor who's a doctor, and we were like, man, like yesterday, it was actually yesterday, we were like, because I was telling him about the class, you know, I was like, I'm so frustrated. And he's like, man, can you imagine if we knew, okay, like when we were in college, beginning college, can you imagine if we would have known what graduate school was going to be like the level of effort that was going to require? Imagine if we used that much effort when we were in undergraduate school, you know? And then it was like, and then once you go post, even beyond that, it's like, man, can you remember like in grad school? I wish that, you know, it's like me asking you to factor something. It's like, God, I wish it could all be factoring now because it's all relatively easy, right? You know what I'm saying? It's all relative. But it's hard to explain to someone who's in the calculus sequence. You have to remember, Cal 3, even though it sounds like big-time math, Cal 3 is only a third semester course. If you start out at UT Austin with Cal 1, Cal 3 is only the third math class you would take. So here it may seem like the pinnacle, but it's just the beginning of a lot more math. So work ethic is so important early. And what's the biggest hurdle that I see at colleges like this? Maybe I shouldn't document this either. Well, this is that was fun. Okay, fundamental theorem of line integrals. All right. We did this one, right? All right, we need to talk about a couple more definitions. I only have like 10, 15 minutes because I've been jabbing away today. But these are important concepts, so let's try and get them down. Path independence. All right, the idea of a closed curve. Make pretty good sense there? Closed curve, start at the same point you end at. Closed path, same initial and terminal points. So, check this out. The line integral over a vector field C, line integral over C of a vector field dr is path independent in D if and only if the line integral is 0 for every closed curve. All right, that's the definition basically that we would use for path independence. What does it mean to be path independent? That means that anytime you try and integrate over a closed curve, any time you do that, you get 0. Okay, then we'd say that is path independent. And as I say here, it's hard to use this theorem because it requires us to test every closed curve, right? Like if I give you a space, two-dimensional, three-dimensional space, and I say, hey, look, is this line integral, is it path independent here? You can't possibly test every closed curve, right? Can't do it. However, we do have this, which is nice. When F is a conservative vector field, conservative meant what? That vector field is the gradient of a scalar function F. Then if the vector field is conservative, it comes from the gradient of a scalar function, but we already know that the gradient of the scalar function dot dr by the fundamental theorem of line integrals is just the endpoints subtracted. But if we're on a closed path, the endpoints are the same, which means this subtraction gives you 0, right? You're starting at any point at the same point, so when you do the fundamental theorem of line integrals, you get 0 at the end. So line integrals on closed paths of conservative vector fields are path independent. Line integrals of closed paths. So any closed path, right? Any closed path, if you try and do a line integral on that closed path and your vector field comes from the gradient of something, it's path independent. Which means it doesn't matter how you get to those 2 points, any curve in between. Yes? Well, let's see what I give you. Yeah, I mean, I may give you a vector field, and you may have to show that it's a conservative vector field. So you have to show that it came from a little f. And we did a little bit of that in the very beginning. Remember, did I do it? No. It was like we have to do integrals. The integral, go back, and then g of something. Don't worry. Stay tuned. Can I answer it that way? Stay tuned. You'll see how things are going to be asked. All right, determining. How do we determine if f is a conservative vector field? How do we determine it? Okay, before we can do it, we have to establish some things. What a region, what a simply connected region is, and what a non-simply connected region is. And here's an example. If I look at this simply connected one, if I take 2 points in this, right? I connect them with any curve. I can shrink the curve down to basically become almost like a straight line segment between the two. What about this one? Let's say I start right here, right? And I draw a curve to come back to it. So let's say I go like this and I come back to that point right there. If I shrink that point down, or that curve down, will it shrink itself down to a single point? Yes? Are y'all? These are regions. These are not curves, okay? Let me do it a different way. Take this right here. If I take 2 points here, or not 2 points, just draw 1 point. This might work better. If I draw a closed path in here, and I have to get back to that, right, closed path, then can you imagine shrinking that path down? If I shrink it down, it would eventually squeeze down to that point. And every time, as I shrink it, it still lives in that region. So imagine me shrinking this down, so maybe it's this now, and it keeps on getting smaller and smaller until eventually it shrinks down to that point. And every curve that I shrink down lives in that space. That's called a simply connected region. Compare that to this region. This, but it's missing a piece right there. Now try and draw a closed curve. Well, what if I draw this curve right here? That's okay. I can shrink that down. It'll shrink down to the point, no problems. But if I draw this curve, try and shrink that down, what happens? That hole stops me from moving to the left and trying to shrink down. Because I can't move through that hole because that hole is not part of the region. It's not part of my space. So do you see the difference between connected and simply connected? All right, we now establish the conditions that we need for a vector field to be conservative. Let F be P of xy, Q of xy. Let it be a vector field on a simply connected region, D. Suppose P and Q have continuous first-order partial derivatives. And suppose that partial of P with respect to y equals the partial of Q with respect to x throughout D. Then F is conservative. So this is what we will do to see if a vector field is conservative, to check if it's conservative. This is a super powerful theorem, because how else would you know if something was conservative? You would have to try and figure out the scalar function it came from, right? This says you don't have to do that. This says all you have to do is check that these two partials are equal. If these two partials are equal, it is conservative. Then you can assume that that theorem we had before will hold. The theorem here will hold. Line integral on closed path, conservative vector field are path independent. Okay, so let's check this. Is this conservative or not? So I have capital F is equal to 1 plus 2xy plus natural log x squared. So according to the notes, if you look back in the notes, this one, we're going to call this one right here P of xy. Is it? Am I doing different? Oh, sorry. I did. Oh. Well, it's okay. I skipped one. I'll come back to the one I skipped. Let's do this one. This is example 3. And then Q of xy. So what we need to check is this. Check to see if the partial P with respect to y is equal to the partial Q with respect to x. So what is the partial of P with respect to y? 2x. What's the partial of Q with respect to x? 2x. I'm done. This is a conservative vector field. Right? It is conservative, right? Now here's the problem, though. I know it's conservative, therefore I know it comes from a little f. In order for me to use that theorem, right, here, where the endpoints, right, right, the fundamental theorem of line integrals says, oh, you don't have to do all that dotting of everything. All you have to do is just evaluate the two endpoints. We need to know what little f is, don't we? Look, we need to know little f right there. If we're given the vector field, here's what we can say. If someone now hands us a vector field, we can say, maybe I can use the line integral, the fundamental theorem. Maybe I can. First thing I'm going to do is see if that vector field is conservative. So I do this test we just did, right? Ah, it is conservative. That means I can use this. But I need to find little f. So now we have to go about the task of recovering it. And that I'm not going to have enough time for today. Okay, I'm not going to be able to recover it. I think that's what the example says, right? This is the one I skipped, right? Okay, that's the one I skipped. Let's just check it real quick. This is P, this is Q, right? What's... What? Oh, you're already giving it to me? Okay. So the partial of P with respect to y is 2x. Partial of Q with respect to x is 2x. It's conservative. The next note says, recall that conservative, if there exists a scalar function f such that the gradient of f is f. So we already know this. That's what conservative meant. In such a case, now we didn't talk about this. In such a case, f, little f, is called the potential function for f. Potential function. It's basically the function that creates the vector field. So we call it the potential function. We now learn how to find potential functions if it exists, and we will use what's called partial integration. And that's something we'll spend the next class on, doing partial integration, which we've done before once. I said we'll revisit that, remember? Well, okay. So I need to come back when we start class. We already know this is conservative, and I need to find its potential function. That's where I'll pick up on Monday.
When is our class?
Yeah. Is it when? It should be on your calendar. Oh, Monday is the last day to drop.